All right, well, good afternoon, everyone. Welcome or welcome back if you are joining us for this, the third session of 4, where today we talk about the weakest link in our buildings, the windows. I know of building engineers or building enclosure engineers who would just get rid of windows entirely. So without going that far, what can we do when the building code clearly requires compliance with all relevant clauses simultaneously? So far in our Knowledge Zone series, on Tuesday, Rob and Ryan talked about B1 structure and how to avoid losing all performance intensive H1 energy efficiency and sort of how B1 overtakes H1 intent, and we ended up with the failure of clause E3 internal moisture, that visible failure known as condensation. So this failure is despite that same design being able to meet the code requirements for B1 and H1 if they're treated in a compliance silo. Yesterday, Dr. Anthony Pelosi, while bringing some viable alternatives, pointed out that gaining compliance with B2 durability using heavy-duty copper, chromium, and arsenic may not be great for the health of fabricators and builders, and anywhere materials with toxins are present, ventilation is key. He showed that G4 calls for fresh outdoor air, but the outdoor air, though fresher than roof space air, is not always that fresh. And so that's just one of the reasons operable windows as your ventilation strategy is not great. Anthony's own home and design now demonstrated how these challenges can be overcome. This ProClimate Knowledge Zone series is about connecting the dots between code clauses. If we tweak one code clause compliance element of a design, something else gets affected. So the first challenge is getting to grips with the high-level code clauses and not starting at the acceptable solutions default. Well, speaking of acceptable solutions, Rob Campion is with us today. He is not the acceptable solution, but he did write one. Rob is the technical manager for the Window and Glass Association of New Zealand. He is most definitely part of the window industry furniture. He is opinionated and direct, and we clearly need that. So today is important for our industry. 8 years ago, led by Rob, we stood as a group around a series of recessed window details here in our seminar space, and we argued through the benefits and drawbacks and market readiness. Now, of course, that work had started well prior. In my opinion, Rob is the most suitable person to be unpeeling E2, external moisture, and H1 energy efficiency today, with clearly a focus on windows. Rob, I'll hand over to you, and if I get some tough questions for you, I'll turn my camera back on and wait for the right pause to jump in, but we'll leave most questions to the end. So here's the first question to preempt the one that many have asked for years, and I guarantee will come up today. Why don't we just install windows like in Europe?
John, that's a really good question, and kind of easy to ask with a bit of hindsight, I suppose, but the reality is we've never installed windows recessed back into the building. You know, we just have a tradition of doing things the way we've done it. And the work that's going on and the work we're going to talk about today is kind of the first step into perhaps moving in the direction you've just suggested.
Well, great, Rob. Over to you. I'll turn my camera off and I'll interrupt you maybe in 10 or 15 minutes or so.
Cool. Whenever you like, John. So,
great stuff.
Rob Campion Tokoingoa. Warm welcome to all of you. And of course, thanks to John and the team at ProClimate for inviting me along today. Just a little bit of background to myself. I started my career in the window industry with a small commercial system manufacturer back in 1985 in New Plymouth. I've been a part of the Window Association since the late 90s and joined them full time when they merged with the Glass Association in 2018, so as their technical manager. So for all my sins, that's what has brought me here today to have a bit of a chat about the building code. And specifically these two clauses, as John mentioned, E2 and H1. As you're all aware, I'm sure, there are 8 primary code sections with 41 individual clauses sitting behind those, of which 13, if we remove the fire stuff, can be applied to windows and doors. Okay, so windows and doors are not all about E2 or H1. There's actually a significant number of clauses that are applied to them in their design and application. It's kind of symbolic that these two icons are set so far apart on the slide, because like most parts of the code, they're typically considered very individually. And so initially, we're going to do the same. And we'll start by having a quick look at E2. So E2, the external moisture clause from our building code, and basically it's regulation that sets out how our buildings should manage external moisture. The functional requirement, and I really like this particular paragraph, the functional requirement of E2 is that buildings must be constructed to provide adequate resistance to penetration by and the accumulation of moisture from the outside. That is exactly what we're trying to do every time we look at a window detail. We're trying to keep the water out and make sure that it doesn't accumulate in that space. Of course, E2AS1 is where the acceptable solutions are listed out and nominated, which of course, and it does look at all junctions of the building envelope, just not those relating to windows and doors. But there's a significant section in there relating to my favorite subject. Okay, so with E2 and E2AS1, there is a bit of a story which I'd like to go through. So, as I say, the intent of E2 is to keep external water on the outside of the building, and we've not always done a great job of that, to be fair. In the early 2000s, it became very public, our $2 billion leaky home syndrome. And with that kind of pressure, the whole of the building industry was compelled to develop solutions to a very public but very, very real situation. At the time, building consultants Prendos published some analysis of their experiences, and actually they were blasted for doing this in the newspapers, for exaggerating the situation, which turned out to be completely untrue. The window industry collectively took note of this information and decided to take control of this particular area, the space between the window and the building envelope, the installation. And we decided that we needed to help out and develop a better method of installing windows, given the pressures that were going on at the time. We considered the 4 Ds. We took what we knew about pressure equalization from curtain wall design, and we acknowledged that we needed to protect the opening, remembering, of course, at the time that the code allowed for the use of untreated timber. At the same time, brands were evaluating the use of cavities between our framing and our cladding, which pushed the window out of the building and away from its framing support, or the support of the framing. So our solution to that was to develop a support bar that not only supported the weight of the window, but also provided adequate drainage and ventilation paths for the window cavity to help that pressure equalization around the window cavity to help keep water out of it. In 2005, we published this as WANS WIS, the Window Association of New Zealand Window Installation System. And at the same time, the DBH, as MB were then, published their version of our details. So we talked to them about the details. There wasn't a complete agreement across all parties. So they published their version in E2AS1, the 2nd edition. And for a long time, I was a bit quick on that one. And for a long time, we actually competed in the market where some councils liked WANS WIS, some preferred E2AS1, and designers had the same kind of issues, I suppose. In 2009, we got together, MB, or DBH, MB, I can't remember what it was at the time. We got together and we rationalized the 2 documents. And in 2011, the 3rd edition, as we know it, was published. So it merged the 2. There was compromises on both from both parties to find one set of details that we've now used for a very, very long time. In terms of H1, the story is not quite as flowery, I suppose, not quite as interesting. Functional requirement of H1 is set out in 1.2. And there's the acceptable solution. So the acceptable solution for H1 has, as you all know, 3 methods of compliance: the schedule, the calculation, the modelling methods. But none of these are new. Excuse me for a moment. None of these are new. Early iterations of H1 mostly made reference straight back to NZS 4218. And in this case, in 2004, the schedule basically allowed for single glazing across most of the country and clear IGUs in the south. In 2009, this was updated to essentially make clear IGUs mandatory across the country, unless of course you were calculating or modeling to use something else, but you know, why would you? This is kind of the date where everybody says double glazing became mandatory. And yes, it was, but it wasn't. And then in 2021, the 5th edition, which we all know very well, of course, was introduced. Along with it, 6 new climate zones, or the country divided into 6 new climate zones, and a significantly increased performance requirements for windows and doors. This step changed our industry significantly. You know, thermally broken frames and high performance low E glazing were no longer optional extras. They were a requirement moving forward. There was, of course, an introductory period that allowed our industry to get up to speed with the material supply issues, but you know, we were all aiming for these new higher performance values. Also introduced as part of the 5th edition was table E111, which gave an improved guidance on the expected performance of frame and glazing combinations. So we took glazing U values and we matched those to the frame types, as I say, to give an expected thermal performance. So the U values were listed out here. These were taken from sort of standard available products. Apply those U values to an aluminium frame and you've got this collection of R values, thermally broken, UPVC, and timber framing. So a really useful tool when you're using the schedule and just trying to understand from a design perspective where you might position your product specification. So again, these 2 clauses are typically considered in isolation, which does start to raise concerns for building designers as they work through their projects. You know, okay, so we want to install the windows in our project in accordance with E2AS1, which is fine when we have a simple window. Okay. But when a better performing window is required to comply with to satisfy the demands of H1, that detail impacts the overall performance of the window itself, because that aluminium support bar, which is doing a job holding the window up, but it's now also bridging the thermal break in the frame. So you're reducing that overall performance, which is obviously not ideal. From a technical and detailing perspective, designing a solid form is pretty easy, right? You know, if you don't need light or ventilation or access, the envelope details become really, really easy. When you do decide you do want light ventilation and access, things get a little bit more complex. In lecturing with architecture students, I've often made reference to taking a sleeping bag, cutting it full of holes, and then covering those holes back over with Glad wrap. Not only have you increased the number of potential leaks in that sleeping bag, but you've also dramatically decreased the thermal performance of its envelope. And this is what adding light, ventilation, and access to your building does. It creates complexity. To respond to that complexity, I refer to the hierarchy of design. Now, a lot of architects like to talk about the form following function or form over function. And I guess the difference between the two depends on how much money your client has. But if we take that equation and modify it slightly to stability over occupation, and this is where stability is about ensuring the integrity and durability of the building itself, which might involve, you know, these particular clauses of the code. The occupation part, so that's follows these clauses. It's about making the building safe, efficient, comfortable, and healthy for its occupants. So, you know, stability is vital, because without that stability, occupation can't occur. And in terms of our clauses, E2 fits with that. And E2 ensures that the building continues to be useful throughout its intended life, and H1 ensures the same for its occupants. In terms of design considerations, when you're looking to develop window details or details of any, you know, when you need to try and consider how you respond to those complex junctions that we've talked about, we go back to the PRENDOS graph, in my experience, water ingress almost always presents itself in the lower corners of a window or door opening. Whenever you go to a home where there might have been a problem, water is present at the lower corners of the frame. And this often leads to the conclusion that the ingress is a result of window failure itself. But when you look at this graph, it's actually grossly untrue. The vast majorities of failure come through the window installation, come between the window and the building envelope, at that connection between the two, which is why as a window industry, back a few slides, that's just where we decided we needed to focus in terms of developing those details for E2AS1. One of the first tools we use in developing an installation detail is to apply the 4 Ds of weather tightness to any situation. So if you started looking at a head detail, deflection is the first D. Okay, so you deflect water away from any potential risk or risk points, right? But you accept that you aren't always going to deflect everything away, and then if water gets in, you therefore need to provide a drainage path to allow it to get out. Apply the same thinking to a jam detail. Again, we're deflecting that water away wherever we possibly can. That's what the scriber in this particular case is doing. But accept that if water gets through, that there is a drainage path to help it get away from the building, or away from the building. Sill detail, really similar. We're deflecting that water away. We're providing drainage paths should water get into the system to allow it out. But when draining away, again, there will always be residual moisture left behind. And so to deal with that or to respond to that, you look at ventilation and drying out that residual water by creating a ventilated ventilation into that space. And the 4th D of weather tightness, of course, is durability, just ensuring that all the materials that you use are durable throughout this whole process. You might also look at the layers of the envelope. Okay, you start with having a quick look at the drainage plane, the line of the air barrier, and then the layers of insulation and where all of those sit. And at that point, you must recognize, of course, that not all of these will always be perfect, okay? And that the final design may require compromise in one area or another. Of course, anything is possible, but that cost versus buildability equation will become a factor. John's already touched on this actually. Back in 2018, early 2018, when we were going through the development work that was leading into, leading on from the 5th edition of development of the 5th edition of H1, Brands called a workshop to consider recessed window installation details. We gathered at ProClima. Submissions had been called for prior to the meeting, and they were received from a wide section of the industry, not just the window industry, but the whole of the building industry. And these submissions were hung around the walls, and a group of building industry people and professionals were asked to wander around and rate them. Rate them in terms of weather tightness, thermal performance, durability, buildability, cost, based purely on the information that was put in front of them. The majority of these details are actually already being used in the marketplace. There wasn't a lot of new detailing or new suggestions within that space. This was one of my sheets, looking at this particular detail. Obviously, in terms of weather tightness, I thought it was okay. Thermal, pretty average. Buildability, didn't like it at all. Didn't comment on the durability, and so this kind of thing was done for all of the options that were posted around the wall. The outcomes from the workshop were analysed, and MB set up a working group to start considering the issue in more detail. Now, pre this meeting, the window industry had actually completed some work, and we offered this work up to MB for consideration. We'd done some design development, some testing, but MB had some concerns about, the work that we presented, and they wanted to address some items very, very specifically. They wanted to address buildability. They wanted an industry review. We've sort of started with that, and that the development of the working group was was required. There was question around the verification method that was being used to assess window installation details. E2VM1 had some very focused details about how you go about the testing. So we wanted to investigate that. And then of course durability. So we're bringing a third building clause all into one detail development, which is kind of unusual. So our work was parked, and we began assessment of some new options. Okay. So as the first initially the working group sat down and we just looked at two frame types. We looked at facing frames and non-facing frames. Now, facing frames are traditional aluminium frames, whether cold aluminium or thermally broken aluminium, and non-facing frames were UPVC. The reason we went away from the material terms is that, of course, both materials have both frame options available. You can buy a UPVC window with a facing, and you can buy an aluminium frame without a facing. So we went down those very specific terms. At this point, we decided not to consider timber joinery. The timber joinery detailing was just so different to all of these. And when you're talking about developing an acceptable solution, timber windows were a step beyond where an acceptable solution might sit, certainly at the beginning of this process. And then we considered two different positions. Okay, so one was where the window was recessed, basically back to the building rack line, or rebated, where a rebate was formed within the wall line and the window was moved to that position. So those four combinations were considered and debated, and in the end we settled on, in terms of an acceptable solution, we settled on just two frame detail combinations, a recessed facing frame and a recessed non-facing frame. So the aluminium and UPVC. Again, rebate details were just too complex to try and weather adequately in terms of an acceptable solution. Lots of to and fro, where details were drawn up, comments were made, they went back and forward in the working group. We talked about it a lot. But we had an idea of where we wanted to go, but we just, we refined and talked and tested. So we got to a point where we confirmed our details. This is what we wanted to do. And at that point, details were drawn for both facing frame and non-facing frame. And at that point, MB commissioned brands for a 6-test program. The initial 4 tests were developmental tests, okay? And then there were 2 final verification tests. And we went through that process and did lots of development work, actually. A standard verification method, you build your test unit, you put your unit in, you test it as it's designed and built, and then you introduce failure and you test it again, and then you do water management tests where you introduce failure, you understand what happens with the water in that failure, and how the wall holds pressure across it. This testing, we did far more work than that. We were constantly pulling things apart, seeing if there was water in places that we couldn't see. The testing was robust, to be sure. So we did a lot of that, went through all of that. In the end, we were actually pretty happy. We got through all of our testing. The details, the final 2 tests proved that everything that we designed did indeed work and worked well. So we got through the E2 part of the testing. And then we moved into trying to understand how the details were going to perform thermally. Okay, so we did some initial modeling. I think there is some more to be done, but the initial modeling sort of, this is what it showed. So this is the thermally broken frame installed per E2AS1, okay? Facing frame aluminium support bar, which you can just see in under here. Okay, so just to establish a base. All right. And the initial modelling showed that, so with the modelling, for those of you who are unaware, we set the outside temperature at 0, we set the inside temperature at 20 degrees, and then understand where the weak points are. And the weak points in each of the details, in this particular model, were all right in the same location at the back of the condensation channel, right against the vertical upstand that holds the glazing. So with a 20-degree indoor room temperature, we had essentially 10 degrees at the weakest point. Where is that? There we go. So interesting point here. The window that we modelled, thermally broken window with a low E 1.1 glass, had a window R value of 0.62. The installed R value of that particular unit, so that was 0.48, which means that we had a 23% drop in performance by installing that window into the envelope. Listed out, these are the temperature minimums and what our FRSI factors look like. Okay. We compare that to our recess detail. Okay. Our temperatures at head and jambs increased 2 degrees, which is reasonably significant. And at those kind of temperatures, you'd actually typically get above a standard dew point. There was a weakness, or there is a weakness down here at the sill. And what that comes about from is that we've got an aluminium sill tray in under here. So with the head and jambs, we removed the air cavity from around the window in the building envelope, and we filled that full of foam right out to the front edge. Okay. But at the sill, because we needed to ensure that the E2 part of this detail would work, so that the second D, that we had drainage, we've used an aluminium sill tray in here, and that has brought temperature right back into the inner face of the building. So we have a weak point here for sure. Interesting though, and like I sort of mentioned earlier, everything about developing these details includes a compromise. So our window went from 0.62 to 0.55. So we did have an overall increase in, an increase in overall performance, or less of a decrease, however you want to view it. And FRSI numbers sort of reflect those temperatures as well. So not a perfect detail, but certainly one that performs better than the E2 version. Have a look at the same for UPVC. Yes, this UPVC frame has a facing because E2AS1 requires a facing. Here, temperatures all in the same place again as well, that point between the frame and the glazing, at pretty solid numbers at 13.5 degrees. So the window, the UPVC window, again with the 1.1 glass in it with an R of 0.79, 22% drop once it was installed per E2AS1. And really good solid figures around the rest of the installation. The recessed version of that, our head and jamb figures stayed almost the same. Slight decrease at the sill, and again, less of a decrease, that's odd, isn't it? Less of a decrease in our installed R value. So when you compare all of that, like I say, the recessed frame, recessing the window back into the building makes an absolute difference. There was just no discounting that. All right, so that's the work we've done. What's next? So, this testing and development of these details is a relationship between brands and MB. So the testing's been done, the reports have been written, everyone is comfortable with that. MB at the moment, as I understand it, are outsourcing the drawing of the details. And I think they're going to go for a more robust detail than what we've seen previously in E2AS1, just to help people understand the buildability of that. So that is being worked through. At this stage, we have no time frame around the release of the details. The Window Association have reached out to MB and asked if we might publish early as an alternative solution before it becomes an acceptable solution. At this stage, that has not been allowed, given that the details are still being drawn and MB is still working through their policy. So, but yeah, that's where we're at.
Rob, I wonder
yes.
if I can just jump in there.
Absolutely, please.
Yeah,
I'm done.
so you're done? That's great.
Sorry.
No, good as gold. Okay, so there's been a string of questions across the time so far, so maybe we can circle back to a few of them. But
yeah, for sure.
Just one for me to begin with. On that PRENDOS graph,
yes.
There was a sample size of hundreds of windows.
Yes.
Why was this? What's your best guess at why this was ignored at the time?
Well, it was a really interesting study, to be fair. You know, this is the work that they had been doing. PRENDOS were in the business of resolving issues. At the time, I think like any major public event, not everyone agreed that there was actually a problem. You know, there's lots of people saying, exaggerating the problem, and other people who were trying to downplay the problem. And I think it was kind of moved past because of that. You know, the fact that, like I say, in the papers, PRENDOS were blasted for exaggerating the situation. But this was a report of what they saw every day. So.
Okay, next question. And just in the last little bit there, this is just a little bit going backwards, but why the aluminium sill tray in the tested detail?
Okay, so the details so in the development work that we did, we used an aluminium sill tray because it exists. We've actually done some other modeling with a PVC sill tray, and it does increase the temperature at that sill. I can't remember off the top of my head what it is, but it certainly does increase it, but it's currently not available. So the way I see this working is that when MB do publish these details, this is when industry will kick in and start offering alternatives to in terms of material use and for things like the sill tray. You know, you will get better performance by changing that from being a cold piece of metal to something else. So industry will pick it up, guaranteed.
Yeah. Okay. So we've got solutions that are really quite old school in one way, being a sloped sill, or with the part of that. Sorry, I missed the second part of that question. Why not flashing tape of some description?
It's not considered robust enough.
Even on a sloped sill?
On a sill, yes. You know, tape suppliers will tell us that they're absolutely durable, but there is a distrust, and that's a harsh word, and I don't mean it to be harsh. There is a distrust in the application of the tape. Okay, so a solid material, solid metal tray is just seen as a more robust solution to a tape. The very early work that we did back in 2002, we started with just tapes. And that's the path that we headed down initially, but the wider industry struggled with that as a concept. Now, bear in mind, of course, John, that this is an acceptable solution. Okay, there is nothing stopping anyone developing a variation of it that just uses a tape. You know, we've modified the verification methods by taking that detail and running it through the VM. It starts to carry the same weight as an acceptable solution.
Right, so that's pretty key. So that's related to this next question then. So facing frame, E2AS1 window detail, forces failure of E3. Should this section of E2AS1 be removed? So what is that? So the detailing, so you pointed out before that E2AS1 is a lot more than just windows. There's a lot of other details there around, flashing depth and apron flashings and all that kind of stuff. But so for windows, so should this section of E2AS1 be removed?
I've never contemplated it at this time. Like I say, these things tend to be looked at in isolation. I do know that, well, I have heard rumoured that E3 is being reconsidered at the moment, and maybe in the reconsideration of that, you know, we look wider and try to understand whether it truly does negatively impact, those details negatively impact.
Right.
So one of the things that's changed, right? So those details were developed 20 years ago, more than 20 years ago, and construction has changed. You know, the way we wrap our buildings and all the products available. You know, maybe it is time to review all of that at some point in the very near future. So I'm not saying it's not on the cards. It's just hasn't been raised for discussion at this time.
Yeah, and look, it's so interesting. Even in your detail there, you used the word and you described the window profile with the condensation channel.
Yes.
And that in itself, we hear about that as being an admission of failure, and it kind of is, right? But it's a nuance. If you look at the wording for E3, prevent accumulation of internal moisture, if you've provided a drainage channel for condensation to be removed from the building, do you comply with E3? Is that really acceptable? And I didn't mean that from an acceptable solution side. I mean, is that acceptable? Is it adequate?
It has been for a very, very long time. But like I say, we're changing the way we construct. Our buildings are tighter. The way in which condensation occurs has changed. I mean, it's still physics, right? But the environment within our building is changing. And yes, it's fair to say that we need to keep up with that. Absolutely. I mean, E3 actually talks about a need for condensation collection if used with single, I can't remember the exact words, but it basically used to say, paraphrasing, you needed a condensation channel when you were single glazing and you didn't need it when you were double glazing. A lot of thermally broken systems do not have condensation channels.
Right, because the expectation is that the frame temperature is high enough to avoid condensation forming.
Yes.
Okay, let's blast through. I'm going to go back to the very top now and get through as many as we can. So under what circumstances does one not require a support bar? So this is right back to the beginning of the presentation.
Yep. So the reason we introduce a support bar is to make sure that the window doesn't sag under its own weight. And at that point, so if an unsupported window, you know, like I say, at the time, with cavities, we were moving the frame out. At the same time, we were introducing double glazing. So there was this concern that with the weight of the double glazing hanging away from the building, the bottom of the frame would droop, and that would put stress on the miters and the joints within the frame. So the support bar was introduced to respond to that. So if the details are providing adequate support to the window, then the support bar is not required. I mean, the one I've showed in there is 55 mil deep. They start at 20. You know, so if the window is largely supported on the framing, which it is with the recess details that we've developed, you know, the support bar is not required. It's an assessment on a case-by-case basis, to be fair.
Right. Okay, why does H1 have Krypton as an IGU option when it does not exist in New Zealand? So I have been told by aluminium joinery producers, and in brackets, maybe somebody telling some porkies. So does it exist?
Okay. So when we developed E111, it was available and then we had our shipping issues, and basically it became very, very difficult to get and very, very, very expensive. So yes, strictly speaking, it is available, but tracking it down and paying for it, they're two different situations. Okay. So typically people will say no to Krypton because it's just too difficult and too expensive.
All right, okay, so you talked about table E111. So that table doesn't consider the size of the window, which makes a considerable difference to the actual installed R value. What was the basis behind creating that table?
So the table was created, so certainly there are models around the world which base everything on one window. And pre-2009, all of our thermal performance was also based on one window, a 1200 or 1500 window with a million down the middle and a sash on one side. E111 was a departure from that, in that we modeled multiple house lots of windows and then put a weighted average across all of those. So the figure that is in E11 doesn't necessarily relate to a single window. It is based on a weighted average across multiple house lots of joinery.
Okay. Yeah, there's probably a bit more to unpack in there. Okay,
Yeah.
let's maybe another time to better understand some of that. So testing, did any of this testing get done on window suites that are now available, like Centrifix?
No, Centrifix doesn't fit into either of those two categories. And the team at APL have code marked it anyway. So it didn't fit within the equation. It was discussed, absolutely, but it didn't fit within the boundaries that we set ourselves for developing this acceptable solution.
Right, and so that code mark will cover B1 and B2 and E2 and H1
Yep.
and E3, yes. And I'm just going sort of building up and moving from the outside to the inside. It will reference all of those.
I couldn't tell you whether it references E3, but it will be absolutely.
Okay. I'm sure it'll have F2.
Those boxes when they did. Yep.
Okay. What if sill trays were PVC and for your aluminium thermally broken recessed detail?
Absolutely. So the only and throughout this whole exercise, even pre the 2018 workshop, we had looked at PVC sill trays. The biggest issue is colour.
Which is not an issue anymore, right?
Not as much of an issue. Well, it still is an issue in that, yes, you can buy coloured films, etc., but we offer 7 million different powder coat colours. So right. If you wanted to use a PVC sill tray, you would start restricting the colour choice for the bulk of the frame. Yes, it'd be more than white and black, sure, but
because there are foil-faced options now as well, right?
Yes, but whether you could, we have issues where people will choose a roof and window colour that supposedly match, but because the processes are different, they don't quite match, and that is sometimes lost in the design of the building when we say we'll go for a film-covered PVC sill tray. But often it's not understood that the colour variation might be unacceptable to the client.
All right, Rob, could you race back to your detail on E2AS1 with your facings? So the question is, E2AS1 requires a facing. That was the in quotes. So that was stated. What does this mean?
I'm not sure what that question means.
Well, let me ask that a different way then. So could you just describe the difference between a window and a window with a facing? What does that refer to?
So, okay, if we just use this image here. So this is a traditional aluminium window, and the facing is this part from here to here. So when aluminium windows were originally developed back in the 60s, what they did was they basically took a timber frame, which was a block of timber, and it was installed into the building. It had a facing nailed on the outside of it to basically cover the gap between the window and the cladding. So very early extrusion design included that aluminium facing, that cover, that lapping component into the frame. Okay. Now a traditional PVC frame doesn't have that here. So this is a facing frame with a leg that hangs over the front. This is a non-facing frame that doesn't have that leg hanging over. So it's basically a square block, not dissimilar to the timber one I've shown here either, actually.
Right, so other wording for that, chair frame?
and I don't know whether this is me, chair frame tends to be more hollow in this space here. But a chair frame, an equal leg chair frame, is effectively a non-facing frame, yes.
Okay, so it's kind of a little bit of a nuance there, but it's about the old shape of a window trying to be replicated in an aluminium extrusion.
Yes.
Without real
Exactly.
purpose. Is there a purpose hiding in there that we can't see?
It's about deflection. It's about covering that joint between. It's about covering this weak space here.
Okay.
That was its intent.
Okay. Well, I
and
can
for whatever
safely say
reason,
that
we've hung on to that for 60 years.
Yeah, that turned out to be a really great question, and I learned something too, so that's good. Do you know if the Prendos report is available online? And if so, let's try and find a link.
No, it's not. Those graphs were, like I say, from 2002 or 2003. I'm fortunate enough to have found copies from when I used them, 20 years ago. But to the best of my knowledge, they're no longer available on the Prendos website. I'm sorry to say.
Right. Right. Do you have? Well, maybe we could say that if anybody else online does have access to that type of research and data, that would be pretty useful to share.
Yeah.
So, do you have any?
Way out of date now. It's 23 years old. It's out of date, but it is the information that we worked from in the development of E2AS1 as we know it.
Right. Do you have any testing data on how external insulation outside of framing impacts the installed window R value? And no, that wasn't a loaded question from me, Rob.
The short answer is no, we don't. The slightly longer answer is that all through this process, we have had external insulation back of mind. It's part of the reason, and I'm maybe speaking out of turn here, and my apologies to any MB staff who are listening in. It was part of the reason that we moved, part of the reason that we moved away from looking at rebated details for now, because using external insulation is actually very similar to the details that you would need to create for a rebate, because you end up with that same situation. Certainly, it's on the cards to look at moving forward. We decided that with this particular case, just recessing the window back was the simplest E2 detail to resolve. Responding to, again, bearing in mind, these are for acceptable solutions. So these are the no-think details. These are the details that tend to be applied when, for lack of a better term, no one really cares. Okay, so to create a detail, an E2 workable detail around rebates and external solution and external insulation is a lot more work. Getting that water out that extra step is just a bit more difficult. So this is the first step in a much longer process, for sure.
Okay. As an alternative to aluminium drip tray at the sill, there is a brands approved plastic extrusion we use as standard. So there are existing possibilities there, sure.
Yep.
That's all good. Why does UPVC window, why do UPVC windows need a sill tray at all? I guess that is that comment around, or that's then a question around how do we tape and how do we seal in all four sides of a window and not expect a drainage or a leakage through the window?
So that comes back to one of the points that I very subtly made earlier in the presentation, in that the expectation from that question, if I'm understanding it correctly, is that the sill tray is about supporting window failure. So one of the guys that we used to deal with at the DBH many years ago, his mantra was that all window miters fail, and therefore a sill tray was required. that is true of both aluminium and PVC windows. You know, it's not a trait strictly applied to aluminium windows, but the sill tray is not there for the window. Most leaks, as I pointed out, come in around the window and gather at the bottom corners of a frame. So that sill tray, you know, very early on we looked at whether it needed to be continuous and whether you just needed a soaker of some kind in the corner to pick up that water that might get in, over the head or down the jamb to help eject that forward. But it's just easier to have a full length sill tray. That way you pick up those vast majority of installation failures. And should there be a window failure for whatever reason, it also collects that. So, you know, the sill tray is actually material agnostic. Timber windows use sill trays. Well, they used to use sill trays in between. Metals, there's always a metal flashing between the frame and the timber window for exactly these kind of reasons. It's not about the failure of the window, it's about the failure of the joint between the window and the building, largely.
All right, let's crack on. And there's a comment about liquid tanking being available. And then an interesting question here from a facade engineer. What's the point of having both sill tray and sill flashing? Does this approach really assist with enhancing waterproofing performance? Now, that's not going to be from, sorry, yeah, that's not going to be at E2AS1 level. That's going to be at you know, engineered facades, so it's a slightly different animal.
So the sill tray and the sill flashing actually deal with two different situations. The sill tray is about picking up water that might enter the window cavity, or the cavity around the window, and ejecting it forward. The sill tray is about making sure it gets clear of the cladding. Some of the early iterations of these details, actually, rather than depositing failure water to the exterior of the building, they deposited it on the back side of the cladding. So the building cavity has two sides, a wet side and a dry side. The dry side is the building wrap and the wet side is the back of the cladding. And so you can potentially have water going down the back face of the cladding if the cladding is of a suitable or durable material. So, however, with these set of details as an acceptable solution, we wanted to take the water to the outside. So the sill tray picks up that water and deposits on top of the sill flashing. The sill flashing takes that water and deposits it on the outside of the envelope. So they do two different things. Could you extrude them as one? Yes. All
right, Rob, we've got a few minutes left and we've got quite a string of questions, so let's speed up a little bit. That's fine. Is it acceptable for windows or sill to drain into the cavity?
Theoretically, yes. Ideally, no. You know, the cavity was not about systemic drainage. It was about dealing or responding to failure. And like I say, some of the early details had a sill flashing that sat within the cavity, so that if water got, you know, into the cavity, it had ejected it or pushed it to the wet side of the cavity. But it's actually, you know, and the VM actually allows that, but morally,
it certainly does allow it, because our sill tapes are feeding into the wet side of the cavity.
Yes.
Sorry, but effectively, well, yeah, onto the wall underlay, if that's a better way to describe it.
Yeah. So morally, we just chose to go to the exterior.
Okay. Has there been any testing on timber windows for facing and non-facing?
Timber windows typically don't have a facing connected. They have an attached board. Certainly, there are companies out there who have done 4211 and VM testing on timber windows, and they pass. Yeah, just the same. Yep.
Okay.
Absolutely.
So I'll jump down to a question again about timber joinery. You touched on timber joinery not being considered the right fit for the acceptable solutions. Is there any intent to add timber joinery details into E2AS1 down the track? So we have some industry standard details regarding timber joinery.
Yeah. To be fair, that's probably a question for MB rather than myself. The discussion is that it's such a small percentage of what we do, it doesn't really fit as an acceptable solution. But There may be work. It's changing, but one of the issues has been that the multitude of timber profiles. If they were more consistent, it might be easier to develop an acceptable solution. But that's a discussion to be had with the A, MB, and B, the timber groups.
Okay. All right. Did the thermal modelling account for different wind zones and the impacts these differing wind zones would have on the results?
No, it did not. The thermal modelling itself, you will have noticed, didn't include any cladding, but the boundaries that were set for the models assumed a partially ventilated space. So there was some pressure on the wrap, but it doesn't take into account the variations of wind zones, no.
Okay. All right. Did you mention sill support bars act as a bridge? Should the sill support bars have a thermal break then? Thermally broken.
There might be one way around it.
Thermally broken support bars. That's a new one for you, Rob.
Yeah, when I sit here looking at that picture now and what a support bar looks like, adding a thermal break might just make it a step too complex. We've looked at other materials. We've looked at putting skins across the top of it, separators.
Yeah, just to separate between the profile of the or effectively the extrusion, because when you put that thermal break, like in your image there, your thermal break is already sitting outside the building line and already a long way away from the insulation, which then is that disconnect for the energy efficiency question.
Yes.
Even though it's a thermally broken aluminium frame.
Yeah.
Okay.
I think much better result just recessing the window back. And to be fair, architecturally, I quite like it anyway.
Rob, there's a few more comment or questions in here. We are going to wrap up though. So for everybody online, if you thought today's session was an important step in our understanding, I encourage you to sign up for next week's session too. Thursday lunchtime next week, we hear from Jason Quinn from Sustainable Engineering, who will challenge our thinking in E3 internal moisture and G4 ventilation compliance. So have you seen with every presentation, no one is able to speak about the two clauses that I've asked them to dig into. They all get carried away and talk about other connected clauses, which I say maybe that's bingo, that's a good result. So I thank you all for your time, and a huge thank you to Rob Campion. Rob, thank you for sharing your depth of knowledge, your hands-on experience, and your clear love of the industry and where it's going. So thank you so much for your time, and we'll see everybody next week.
Thank you, John. Thank you, everyone.